All right, welcome to our 8th lesson in modern physics. In this one, we're going to go over quantum spin and what it actually is. I know a lot of you have done quantum spin in chemistry, mainly assigning it things like up or down, things like that. But what it actually is, we're going to go over. Now, to first understand quantum spin, I think we need to take a little introduction. Hold on, my PowerPoint's not changing. There we go. A little introduction to classical spin. Classical spin isn't part of the curriculum, but I think it's really important to understand it in order to figure out what quantum spin actually is. So I believe you've actually done torque in calculus class. Right? And torque is just the cross product between force and the position to a rotational axis. Okay. There is a right-hand rule for torque, just like there's a right-hand rule for any cross product. Right? Another example is linear momentum. So we've talked about, angular momentum. We've talked about linear momentum, which is P equals mv. Angular momentum is given the symbol capital L, and it equals moment of inertia times angular velocity. So you can understand what angular velocity is. It's the speed at which you're spinning. Okay, and the units are radians per second. Okay, moment of inertia, however, is analogous to mass. Okay, it's not mass, but for example, if you had a truck, right? A truck has a lot of mass, right? And so it has a lot of inertia. It's hard to change that inertia. If the truck was moving at a certain speed, it's harder to get it to change it. Moment of inertia is the same thing. It's just for rotational motion, right? Whether or not it's hard or easy to cause something's rotational motion to change. I'm not going to go over too much as to how to calculate moment of inertia, but just understand what it is actually used for. And lastly, just like linear momentum is conserved, angular momentum is also conserved. And you can think of them as completely separate. Linear momentum is independently conserved and angular momentum is independently conserved, right? They're not conserved together. They're conserved separately. And here's an example. If you've ever seen figure skaters, right? They've got their arms out. When their arms are out, right, they actually have a very large angular momentum. When their arms, no, sorry, not a large angular momentum, a large moment of inertia, right? And when they bring their arms in, their moment of inertia decreases. Now, in order for angular momentum to be conserved, if their moment of inertia decreases, right, their angular velocity must increase, and that's why they start spinning fast. All right, now just like when we talked about impulse, right? We say that impulse, which is your net force acted over some time period, equals a change in momentum. Just like when we talked about that, right? This is analogous to that. This is Newton's second law for rotational motions, where a torque, right, or the sum of all torques applied over some time t equals a change in angular momentum. Now, usually I like to do my demonstrations with the wheel, just like this picture here. But I don't have that wheel, it's at school. But I did find a good YouTube video that where someone does it on YouTube. So I will post that as well so you can see it. And it is important to understand that because it goes over a very important concept called gyroscopic precession. And gyroscopic precession is what's important in understanding quantum spin. So let me just quickly explain what gyroscopic precession is. Okay, so I just went and got my globe. So here's the Earth. Now the Earth undergoes 3 types of rotational motions. Right? The first is a revolution around the sun. Okay? Of course, you have a rotation about its axis. Okay, and then you have precession. What's precession is it does this. It wobbles, right? Just like a spinning top wobbles around, right? And we don't actually perceive that. It doesn't affect our daily lives. And why? Because for one full wobble, it takes about 20,000 years compared to 1 year and 1 day, right? 20,000 years. That means that in 10,000 years, in half that time, the orientation will go from this to this, which means we will have summer in January and winter in July, at least in the northern hemisphere anyways. So that's what precession is, gyroscopic precession. Okay, so before you continue on with this video, I do want you to pause it because gyroscopic precession is a difficult concept, and go watch that YouTube video that I posted on gyroscopic precession. Right? Or go look up gyroscopic precession yourself. It's important for understanding quantum spin. So pause the video or come back to this point in the video later. Okay, so I'm assuming you've gone and done that now. And we are going to move on to talk about quantum spin. Now, elementary particles all have a variety of physical properties. You have mass, right? Electrons have a mass, right? They have a charge. Okay, that's another property. Size, color. Color is another property. You've never heard of color, but quarks have a color charge. Okay? And does that mean quarks have a color? No. Right? Does an electron have a big negative symbol on it? No. Okay. It's just a name that physicists chose to assign a certain property they were observing. They had to explain this property. Right? Then they had to assign it a name. They had to look at how that property interacts. Right? And it turns out that charges have a property where you have two different charges. Okay? Right? And you just labeled electrons negative and labeled protons positive. And everything is built off of that convention. And the important thing is not understanding the name, but understanding the properties that exist within that name. Okay, so yes, quarks have a color charge, and they can be one of three colors, right? But we're not going to talk about that. If you're curious, there's also a property called strangeness, right? Fundamental particles have a property called strangeness. Why? Physicists observed that they had some sort of strange property. And with great naming skills, they decided to name that property strangeness. All right? So don't worry about that. It's just a name. Now, in 1922, Otto Stern and Walter Gerlach performed an experiment. Okay, and I'm going to actually have you perform this experiment as well, through an online simulation, of course. But it demonstrated that electrons have an intrinsic magnetic moment. What does that mean? Well, it means quantum spin, and that's what this whole lesson is going over. What does quantum spin mean? What is an intrinsic magnetic moment? Okay, and it took until 1927 for Wolfgang Pauli to formalize this theory of quantum spin, right? And using the Schrödinger equation, which again, I just briefly showed you the Schrödinger equation in previous class. It's okay. And you've probably heard of in chemistry class the Pauli exclusion principle. We're not going to really talk about the Pauli exclusion principle. We're just going to explain what spin is. And to do that, we're going to look at the stern-gerlach experiment. So, what's the stern-gerlach experiment? Well, let's look at this. Let's say you have a magnetic field. Okay, top, north, bottom, south, and in between it's just a homogeneous magnetic field, meaning it's the same, this field strength is the same at one point here as another point here. Okay, it's just a non-changing magnetic field. Then we're going to put a magnet and we're going to have it go across, just like this. And that is what's going to happen. Pretty predictable, right? Let's go back to that again. If you look at it, here you have the north side of the magnet up here. It's going to want to repel from this magnet here, and that's going to push it down. Similarly, the south side will want to repel from that side, and that'll push it up. And so the entire magnet will rotate like so. Okay, well, what if this magnet were spinning, right? Just like, hopefully you did go over the gyroscopic precession video, but just like when you had the wheel and it's spinning, right, and you let it drop, the wheel didn't actually fall. What happened to it? It stayed up, but it started to rotate around like this in order to preserve what? Angular momentum. Right? Remember, conservation of angular momentum. Okay, so what do you think is going to happen in this case? Well, it's going to precess. It's going to undergo gyroscopic precession. Okay, sorry, I don't have an animation to show that, but it's going to undergo that gyroscopic precession. All right, and it's just going to pass straight through. So let's look at another example. This is an inhomogeneous magnetic field. Notice that I've written that the north magnet on top is strong and the south one on the bottom is weak. Now we still have that magnet spinning, so when it goes through this magnetic field, it will undergo gyroscopic precession. But not only will it undergo that gyroscopic precession, you will have a larger downward force than an upward force. And so what's going to happen is it's going to slightly move on a downwards arc. It's still going to precess, but instead of our first example where it just precessed and went straight, right, it's going to precess on a downwards arc like that. And now you would assume, right, that if you did this with electrons, that depending on that spin, depending on its angular momentum, you would get a variety of different positions. Right? What I mean by that, let me draw. Okay, so let's say you had a screen, and here's your magnets, your north and south magnets. Okay, now if you're sending electrons through, now electrons, they could have angular momentum, they might not. Let's just look at what happens. What happens is, you would assume that if it's weak, it might do something like this. If it's stronger, or maybe it'll go in this direction, and you'll get many different positions of your electron hitting the screen, right? Depending on the electron's angular momentum that you throw through there. But what happened was, we didn't get it at many different positions on the screen. What Stern and Gerlach observed was only 2 positions on the screen. Only ever 2 positions. And so it seemed like, they had angular momentum, because if they didn't have angular momentum, they wouldn't go down or up like that. Right? So what's happening? We'll just move forward. So it turns out what's happening is they have some sort of spin which is quantized. You can only have 1 or 2 values for electrons anyways. And for all fermions, they can only have 1 or 2 values. We'll talk, I think you probably learned what fermions are in chemistry. We'll talk more about that when we get to particle physics. But you can only have 1 or 2 values. And we named these values plus 1/2, minus 1/2, or up spin and down spin. Okay, and we call it spin, but really this doesn't mean the electron is actually spinning. In fact, the electron's not actually spinning. But what happens is it has some sort of internal or magnetic property to it. And because it has some sort of internal magnetic property, which we call intrinsic magnetic moment, it is interacting with that magnetic field in only one of two ways. And that is what spin is. It's an intrinsic magnetic property. It's a magnetic property, not an actual spinning object. Okay, so in classical physics, when you look at the bicycle wheel, that is something that's actually spinning. That's not how it's actually working in quantum mechanics, but it's definitely a good visual, which is why we call it spin in the first place. Okay, so electrons, for example, are fermions, protons, neutrons, quarks, and they have either an up or a down spin. Bosons, however, which we'll talk more about bosons, but like photons, gluon, WZ bosons, right? They actually have a spin which are quantized into one of three groups, right? And so we have 1, 0, and -1. And then other particles, again, we have 3 halves, 1 half, minus a half, and minus 3 halves. Okay, and so on. Now fermions, which can only have a half spin, right? This is the Pauli exclusion principle that you learned about in chemistry. You cannot have two spins in the same state, right? So you can't do that, right? And so it fills up like that. However, the Pauli exclusion principle is only true for fermions. Bosons can occupy the same quantum state. So what you can do, even though this example on the left is currently in the lowest possible state there is, because you can't fill up fermions with two states in the same level, bosons we can. So if we drop this low enough to everything goes into that bottom state, that's what is called a BoseEinstein condensate. Okay, and it's considered a state of matter, but we're not going to really talk about that. I just thought that was interesting. Okay, so hopefully you sort of get an idea for what quantum spin is. Definitely read over the handout. Front and back, there's more information than I've talked about, which is quite interesting. But the main thing I want you to get from this is what is quantum spin. And therefore, tomorrow I'm going to assign you the lab of the stern-gerlach experiment. Now, when you're doing the lab, it's important to understand wave-particle duality, okay, and polarization, how I explain it with polarization, because I am going to sort of use this stern-gerlach experiment as an analogy with our polarization experiment that we did. Well, thought experiments that we did in that long lesson. All right. Good luck. Ask me questions if you have them.